Look around. Everything you see, the ground beneath your feet, the devices in your hands, the neurons firing inside your skull, is an elaborate structure built from simple parts, atoms. We take their existence for granted. They are the fundamental building blocks, immutable and persistent. But the stability of the atom, this basic chemical memory, was not always guaranteed. In fact, for the first hundreds of thousands of years of existence, the universe was actively fighting against the formation of even the simplest atomic structure. The cosmos we inhabit today is a masterpiece of complexity, a billion-year accumulation of successful information storage. But all of this, all of us, rests entirely on one single quantum victory. The moment the first proton and electron successfully decided to stick together and form the hydrogen atom. It was the universe's first breath of coherence, and it fundamentally changed physics, structure, and the very possibility of light. What if atoms were never meant to exist? What if the universe failed at this simple task? Our story begins when the cosmos was still too young, too hot, and too chaotic to allow for history. Imagine the universe at a specific critical point in its infancy, approximately 100,000 years after the Big Bang. The temperature is overwhelming, tens of thousands of degrees Kelvin. Matter does exist, but not in the neat, organized form we recognize. Instead, the entire cosmos is filled with a hot, ionized, uniform soup, a plasma. This plasma consisted mainly of free protons and neutrons, collectively known as baryons, along with swarms of free-floating electrons. This was the universe in a state of high-energy perpetual motion, a frantic, disorganized chaos. Crucially, in this environment, light could not travel. Photons, the particles of light, were constantly interacting with the charged free electrons and protons through a process called Thomson's scattering. Every time a photon tried to move, it was immediately intercepted and knocked off course by an electron, preventing it from traveling any significant distance. If one could have looked upon the universe at this time, one would have seen only an unbearable, featureless white glare. It was an infinitely thick, pervasive cosmic fog. This opacity was more than just a visual impediment. It was a fundamental barrier to cosmic structure. Since light was constantly trapped, colliding with matter and immediately re-radiating, the light itself exerted massive outward pressure on the matter. This overwhelming photon pressure prevented gravity, the force that drives all structure, from ever achieving dominance. Without the ability to see or organize itself, the universe was functionally blind and structurally paralyzed, stuck in a state of uniform, energetic infancy. This inability for light to escape and carry spatial information meant the conditions for complex memory were absent. The energy of light was the jailer. The great engine of change in the early universe was simple: expansion. As the universe inflated, the volume increased and the temperature of the contents dropped steadily. For hundreds of thousands of years, this cooling made little difference. The average photon still contained enough kinetic energy to strip an electron from a proton almost instantaneously if they briefly coupled. Any momentary atomic connection was immediately broken by the chaotic, searing heat. The high kinetic energy of the particles guaranteed failure. But the cooling continued. When the universe reached approximately 379,000 years of age, the temperature had finally dipped below the critical threshold of roughly 3,000 Kelvin. At this temperature, the average energy of the ambient photons was no longer sufficient to maintain the ionized state of hydrogen. The quantum binding forces of the nucleus were finally gaining the upper hand over the chaotic thermal energy of the environment. The stage was set for the most profound phase transition in cosmic history. This moment, known as the Recombination epoch, saw the universe's massive supply of free electrons become permanently bound to protons, forming the first stable neutral hydrogen atoms, along with some neutral helium. The formation was not trivial. It was a delicate quantum mechanical balancing act. Electrons attempting to settle into the stable ground state orbital typically emit a high-energy photon known as a Lyman series photon. In the dense environment of the early universe, that emitted photon would simply travel a short distance and immediately reionize a neighboring atom, collapsing the newly forming structure and returning the universe to its chaotic state. This posed an immediate challenge to atomic stability. The universe required a quantum mechanical workaround. It found one in the subtle process of two-photon decay. By emitting two lower-energy photons simultaneously, the electron could drop to its stable, lowest-energy state without producing the single, destructive high-energy photon that would undo the work of binding. This sophisticated quantum process guaranteed the survival of the neutral atom. This required stability, therefore, was not a passive state, but an active, dynamic one. The detailed physics confirms that the atom is not just a static entity, but a system that actively fights entropy. This transition was the universe's first successful system of information retention. The formation of neutral hydrogen was the triumph of persistence over chaos, establishing the foundational system upon which all subsequent complexity would be built. The immediate and radical consequence of recombination was decoupling. Once the electrons were bound into neutral atoms, the neutral matter ceased to interact frequently with the photons of light. With matter suddenly transparent, the photons that had been trapped for hundreds of thousands of years were finally free to stream across the cosmos unimpeded. This moment, occurring around 379,000 years, was the universe gaining sight. The light that was released is the most ancient observable radiation we can detect. The cosmic microwave background, CMB. The CMB is the instantaneous photographic evidence of the universe's previous plasma state, capturing the cosmos exactly at the moment it transitioned into transparency. The sheer fact that this ancient light can reach us proves that the atoms successfully held themselves together and lifted the cosmic fog. The release of this energy was simultaneously the end of the light's dominance and the start of a new, structure-driven era. Following this grand revelation, the universe entered a strange and profound period known as the Cosmic Dark Ages. The universe was now transparent, but paradoxically, it was dark. The darkness was not absolute, but it was visually true from the perspective of an observer attuned to visible light. Although the universe was flooded with a light released during decoupling, the continued relentless expansion of space immediately stretched and cooled the wavelengths of the CMB photons, shifting them rapidly into the low-energy infrared spectrum, invisible to human eyes. Furthermore, no stars had formed yet to create new sources of visible light. For a hypothetical observer, the universe became a featureless void of profound quiet. This quiet was not stagnation, however. It was a period of intense gravitational incubation. The removal of the photon pressure that had previously held matter in a uniform state meant gravity was finally the undisputed architect of the cosmos. This period, lasting for tens of millions of years, saw the focus shift from high-energy radiation physics to the slow, relentless shaping of mass. Gravity began the work of collapsing the vast, neutral clouds of hydrogen and helium gas into the first structures. The structures that gravity began to assemble were not randomly distributed across space. They were guided by a vast, invisible map imprinted at the very moment the atoms formed, the baryon acoustic oscillations BAOs. Before decoupling, sound waves propagated through the primordial plasma. Any overdensity of matter, often anchored by a concentration of dark matter which only interacts gravitationally, would attract more baryons and photons. However, the intense pressure from the trapped photons would immediately push the baryonic matter and photons outwards, generating a spherical acoustic wave moving at a high velocity. The crucial action occurred when the first atoms formed during the recombination epoch. The sudden transparency relieved the photon pressure that was driving the acoustic waves. The outward movement of the baryonic matter was instantly frozen in place, solidifying the wave structure into a vast, residual shell of overdense matter. To visualize this, imagine dropping a pebble into a calm pond. As the ripple expands, imagine the water instantly turning to ice at the precise moment the ripple reaches a specific radius. That radius is the sound horizon. This specific distance, approximately 490 million light-years in the modern universe, is now locked into the large-scale distribution of matter. These frozen shells of matter, coupled with the dark matter remaining at the original overdensity center, acted as the initial gravitational seeds. Cosmologists treat this preferred separation distance of galaxies as a standard ruler, allowing precise measurements of the universe's geometry and expansion history. The stability of the neutral atom was the precise quantum mechanical mechanism that locked this cosmic blueprint into place, ensuring that sound was transformed into the enduring architecture of the cosmos. The cosmological timeline clearly demonstrates that atomic stability dictates the physical structure and clarity of the universe across 4 distinct consequential eras. The sequence underscores that the formation of the atom was the causal link necessary for the transition from a smooth, pressure-dominated environment to a structured, gravity-dominated one. The successful formation of the neutral hydrogen atom established more than just a new chemical state. It laid the foundation for information and persistence in the cosmos. The fundamental question is why this new structure endured when the previous plasma state was one of constant, self-erasing interactions. Advanced theory suggests that atomic stability functions as a form of primitive memory. The electron waveform stabilizes in specific orbitals, and the system resists immediate decay not by being static but through dynamic reversibility. This means the atom acts as a feedback loop, where the electron cloud and nucleus co-maintain a mutual coherence, constantly restoring their structure against external thermal threats, the ultimate form of persistence against entropy. Had the electron and proton failed to negotiate this stability, all matter would have instantly dissolved back into chaos. No molecules could form, no complex chemistry could evolve, and no stable structures could accumulate mass over the vast timescales necessary for stellar formation. The atom's capacity to retain its structure against thermal pressure is the prerequisite for all subsequent complexity. The atom is the universe's first successful information-retaining structure, ensuring that events could leave an imprint that lasts longer than a nanosecond. The existence of the stable atom provides the critical foundation for complexity and consequently the observer's arrow of time. While global thermodynamics pushes toward entropy and information loss, the formation of the atom introduces a crucial local exception. The atom's persistence, functioning as a phase-locked memory loop, allows matter to engage in thermodynamic processes that lead to increasingly complex organizational states. The sophisticated evolution from simple atoms to complex molecules, and finally from molecular structures to the highly complex, memory-driven structures of living neurons, is not a collection of isolated events. It is a continuous, recursive sequence of building structures that amplify the ability to store information. Our entire infrastructure of consciousness, our ability to remember history, calculate the future, and analyze the Big Bang itself, is built upon the foundational, stubborn persistence of the stable hydrogen atom, which secured its internal information structure against the violence of the early universe. For over 100 million years following decoupling, gravity worked silently and relentlessly in the Dark Ages. It pulled the vast, neutral clouds of hydrogen and helium gas into the density peaks established by the frozen baryon acoustic oscillations. By the time the universe reached an age of approximately 150 million years, the gravitational collapse in these overdense regions had reached critical mass. The material ignited, forming the first generation of stars, population III stars. These celestial bodies were unique in their purity. They were formed solely of the primordial elements created during the Big Bang, hydrogen and helium. Because they completely lack the heavier elements, metals, that facilitate efficient cooling, these first stars formed exceptionally massive, often spanning a mass range between 100 and 300 solar masses or more. They were short-lived, brilliant behemoths that burned fiercely and briefly. Their intense heat and power served one final, transformative purpose: to tear apart the very neutral medium that created them. The enormous, hyperluminous population III stars produced massive quantities of high-energy ultraviolet UV radiation, primarily in the Lyman continuum. This light was energetic enough to overcome the delicate stability of the surrounding neutral hydrogen atoms, stripping away the electrons and reverting the intergalactic medium IgM back to an ionized state. This process marks the epoch of reionization (EOR), a cosmic phase transition that occurred roughly between 150 million and 1 billion years after the Big Bang. The very atoms that had brought clarity and structure to the universe were now systematically destroyed by the light of the structures they enabled. As more stars and early galaxies formed, these pockets of ionized gas expanded outwards, creating massive bubbles in the surrounding neutral IgM. Slowly, these bubbles merged until the entire cosmos transitioned back to being fully ionized, though now warm and dilute rather than hot and opaque as in the early plasma state. This reionization ended the Dark Ages forever. Once completed, astronomical data suggests completion around redshift Z 5.3. Light could travel freely and permanently across truly vast distances without being immediately absorbed or scattered by neutral hydrogen. The initial creation of the first atoms was followed by their large-scale destruction during reionization, a cycle that proved essential for cosmic maturity. The short, violent lives and deaths of the massive population III stars, many ending in spectacular supernova or parent stability supernova events seeded the cosmos with the first heavy elements, or metals. These elements, created through stellar nucleosynthesis, were incorporated into subsequent generations of stars, population II, and ultimately population I, like our Sun, and formed the basis for rocky planets, complex chemistry, and the possibility of life. The stable atom was the key to stability. The self-sacrificing star was the key to chemical diversity. The vast, intricate cosmos we observe today, with its glittering galaxies clustered in immense filaments and voids, remains an echo of that primordial atomic victory. The complex geometry of the cosmic web is not arbitrary. It follows the map laid down by the frozen sound waves, the baryon acoustic oscillations, which were only stabilized by the instantaneous formation of the first neutral atoms. The stability of the atom, born from a subtle quantum mechanical negotiation against chaos, was the foundational success that allowed structure, gravity, time, and light to flourish. Every atom of iron in our blood, every atom of oxygen in the air, and every intricate molecule that constitutes our consciousness owes its very possibility to the moment, 379,000 years after the beginning, when the simplest particle configuration achieved stability. The universe is not just filled with atoms, it is built on the enduring memory and successful persistence of the first one.